In 3.3, multiplying microbes, we're looking at a biology situation, a very classic problem in math and science that's talking about bacteria and how it's reproducing. So number one, in a biology lab, 500 bacteria reproduce by splitting. Every hour on the hour, each bacterium splits into 2 bacteria. So let's get an idea of what this pattern looks like by completing this table off to the right. At hour 0, right? Hour 0 means we're starting. So this is our initial. At hour 0, we have 500 bacteria. After 1 hour, those 500 are each going to split into 2. So that means we've got now 1,000. And I did that by doing 500 times 2. Now at hour 2, those 1,000 are now going to split and create double the amount, which is 2,000. And I did that by taking 1,000 and timesing it by 2. In hour 3, we're going to take our 2,000 and we're going to multiply that by 2. So 2,000 times 2 is going to give me 4,000. Now be careful, they are skipping from hour 3 to hour 6. So if I went off to the side and did some math, just to kind of find those fill in the gaps, it might help. So in hour 4, we're going to take 4,000 and double it to give me 8,000. In hour 5, we're going to take the 8,000, double it to give me 16,000. And then hour 6, we're going to double 16,000, which is going to be 32,000. So we'll go ahead and figure that out. So 32,000, and we figured that out by doing 16,000 times 2. Now T, hour T, what does that mean? Essentially what that's asking you is, can you write an expression so that whatever number I give you for T, whatever hour, whether it be 1, 2, 6, 10, 18, whatever number I give you for T, could you just drop that number in for T in your expression and it will give me the amount of bacteria? So it's kind of hard to write an expression when you keep taking a previous amount to get the next amount, right? So I got 2,000 by doubling 1,000. I got 4,000 by doubling 2,000. And you notice I had to go off to the side to figure out 4 or 5 to help me with 6. So in math, we really like to figure out how to write an expression based on the initial amount. What are we starting with? So I'm going to erase this and rewrite it. But I'm going to rewrite it all based off of the initial amount of 500. So how can I get 1,000 using the 500? Well, that's kind of easy. 500 times 2 is going to give me 1,000. But how can I get the 2,000 using the 500? What did I multiply 500 by to get me 2,000? 4. How can I get the 4,000 using 500? You might see a pattern here. 500 times 8 is going to give me that 4,000. And what did I do for 500? What did I multiply it by to get me that 3,200? Well, I can always divide that to figure that out. 3,200 divided by 500 is going to give me 64. So you might start to see, let's see if we can figure out, you might start to see a pattern here from 2 to 4, 4 to 8, 8 to 64. We'll come over here too if we want. This is 500 times 8,000 divided by the 500. That's what I thought. 8,000 is 16, right? Divided by 500 is 16. So 2, 4, 8, 16. 500 times what gives me that 16,000? So 16,000 divided by 500, that's 32. So you're going to start seeing a pattern here with the 2, the 4, the 8, the 60, the 16, the 32, the 64. Those are all powers of 2. So I can write my expression as 500, because that's my starting amount, times 2, to the t power, right? This is 2 to the first. Another way to write 4 is 2 to the second power. Another way to write 8 using that 3 is 2 to the third power. Another way to write that 16 is 2 to the fourth power. So 2 to the fourth power. Another way to write the 5, and you're starting to probably see the pattern here. Another way to write that 64 is 2 raised to the 6th power. 1, 2, 3, 6. 1, 2, 3, 6. And if we go back to the initial stage, another way to write 500 is 500 times 2 to the 0 power, because anything to the 0 power is 1. So this is a good expression that we could use, and I can now figure out at any hour what my bacteria is without having to know the previous hour amount. So that's 500 times 2 to the t. So that's just an expression, right? An equation. That's not too bad. The equation n, the number of bacteria, to t, the number of hours. So hours is going to be t, number of bacteria is going to be n. So n is equal to 500 times t to the 2 to the t power. So here's my equation. Use your equation to find n when t is 0. That's pretty simple. Just plug 0 in for t. N is equal to 500 times 2 to the 0 power. Anything to the 0 power is 1. 500 times 1, anything times 1 is itself. So you're going to end up with 500. Now you haven't seen us write you haven't seen us write equations yet, kind of, for these exponential growths. So I want you to start thinking about, what could be my base and how I can use that base to help me get my powers. For number 2, in a different biology lab, a population of single-cell parasites also reproduces hourly. An equation which gives a number of parasites p after t hours looks very similar to our one up there, right? In this case, p is parasites. We've got the 100 times the 3 to the t. Explain what the numbers 103 mean in this situation. Well, if I look at this equation, and I see that it's, again, representing growth, and I start to look at it in the context of number 1, I hope you will understand or kind of see that 100 definitely has to be the initial amount of parasites, because 500 was the initial amount of bacteria. So 100 is basically our initial amount of parasites. So what's the 3 represent in this situation? Well, the 2 was there because every hour the bacteria was doubling. It was splitting into 2. So in this situation, the 3 is telling us how we're growing. It's called our growth factor. And what this means, every hour, our parasites are multiplying, or basically tripling. That means you multiply by 3.